Let us discuss about what is the term e. In natural logarithm, we use this term as log of x to the base e. Now what is this e? This e is termed as Euler's number. Euler was a scientist, and then we also call this as Napier's constant. Now this Euler's number or the Napier's constant can be calculated by using the concept of a compound interest. Now the formula of compound interest is A is equals to P into 1 plus R by n to the power of nt. This is the formula for compound interest, where P is the principal amount, that is the amount which you pay, R is the rate of interest, N is the frequency at which the interest is calculated, and T is the duration for which you are getting the loan or the borrowing, whatever it is. So now the concept of the Euler's number, the concept of E, starts from a matter of fact that we have been talking about exponents and we have been talking about logarithms. So let us take there is a value of 3. Now when you put a power on it, x, this number changes. And mostly if you apply the correct logarithm or if you apply the correct powers, it increases. This is called a growth. Or when you increase the value of x, if you increase the value of x to like 1000, 10,000, then that growth is called as exponential growth. Now we will be talking about a thought project or a thought concept where we take an example of a bank. Let that bank be an X bank. Now this bank gives you 100% interest. Let us suppose an ideal bank which gives you 100% interest on your deposits. So if I deposited suppose 100 rupee, after 1 year I will get 200 rupee. So it gives us 100% of interest. So as we know, P is principal, R is rate of interest, and is the frequency. Now we will start the idea by taking a simple principal amount to be rupee 1 rupee. So I deposit 1 rupee in a bank account and let the rate of interest be 100. So if it is 100%, then 100 by 100, that is equal to 1. And let the time period be 1 year. And the n over here, because the banks or wherever you have to calculate compound interest, we calculate it in the number of time periods or intervals. Suppose we want to calculate it for 1 year directly, so that will not be compounded, simple interest. So here it will be 1. When you put these values, let us say we have to calculate the interest for 1 year. Then we will get A is equals to P gets 1, R is 1, so it will be 1 plus 1 by 1 to the power 1. That is 1 plus 1, 2. Very basic, very common, that if you have 1 rupee for 1 year at a rate of 100% interest, then you will get 2 rupee at the end of the year. That is correct. Then let us suppose they compound the same. Now see, if you get for 1 year you are getting suppose 100%. Can we divide this into 6 months and 6 months? You are compounding it at 6 months. It means that you will get 2 intervals over here. So we have 6 months. Now it means that they are calculating the compound interest at 6 months. Then the time still remains 1 year, but here the n becomes 2. Why? Because the time is 1 year, but we are calculating the compound interest at 2 intervals. Then what happens? We get A is equals to 1 plus 1 by 2 to the power nt, right? So this becomes 2. So this is 3 by 2 whole square. So this is 9 by 4, that is equals to 2.25. Now here something interesting can be noticed. If you have the same 100% interest at just once in a year, then you get 2 rupee. But when you compound it at 6 months, then you will get 2.25 rupee. So you get an additional 0.25, that is 10%. 10% more than this value. That is a very good growth. Now suppose instead of doing it for every 6 months, let us suppose they compound it every month. The bank compounds your amount, the bank compounds your deposit every month. then this will become 12 months. Then A becomes 1 plus, why am I not writing P? Because P is the principal value, that is 1. So A becomes 1 plus 1 by n value, here n value becomes 12. 12 to the power 12. This value after calculating we will get 2.61 something. This will be the value for the when your 1 rupee is compounded every month for 1 year. Same, it is 100%, same the duration is 1 year, but we are compounding it multiple times. Every month we are calculating the same interest. Then after 12 months, let us suppose the bank calculates or it generates the compound every single day for 1 day. So each day it is calculating the compound interest for that same 1 rupee. Now here A becomes 1 plus 1 by, for 1 day per year. So since the number of terms is 1 year, the n becomes 365. This becomes 365 to the power of 365. This value is hard to calculate normally, but if you calculate the value, we will get it as 2.714 something. This value is very close to the value of E. I'll tell you more about it in a moment, but here we have the value for 1 day. Now till here, what did we understand? We understand that if you take just these two examples, here we have 2 and here we have 2.25. When we increase the number of times to be compounded, so here we compounded it once per year, now here we are compounding it twice per year, then we get an increased gain of 10%, that is 0.25. When I increase it to 12, then still I get a gain from 2.25 to 2.61, that is almost a 0.4, almost 0.4 gain we are having. Now when I am increasing the number of terms from 12 to 365, that is a very large jump, but if you see the gap between this is not less than 0.10%. So 0.10. Now this is a very interesting concept over here. We were increasing the number till 12, then we saw that the growth was good. We are having a good and considerable growth. But after increasing it from 12 to 365, the growth slowed down. Now what mathematicians did, or what Euler did, that instead of taking any amount as base, now forget the concept of bank or interest or whatever it is, when we take the value of A to be 1 plus 1 by infinity to the power infinity. Why did we do that? Because we want to find till what limit can we increase the value of 2. Like Euler wanted to find out that if I give 1 rupee, suppose the thought experiment, that if I give 1 rupee to a bank and if I try to compound it like into an infinitely large amount of periods, then what is the maximum amount that I can get in 1 year? So infinity is not an actual concept, because in mathematics infinity is nothing but an imaginary concept. Let us take a very large number, suppose 10 to the power 5 or 6, 10 to the power 5. Then this answer comes 2.718 or so. Now did you see the difference over here? We increased the number of times for compound from 365 to 10 to the power 5. That is a very enormous jump. But here we expected an enormous jump because even we increased the power. But the actual value increases by 0.004. This concept is actually called as the concept of Euler, or this is called as the concept of Napier. So from here we took the following thought. We thought that if we take an compound interest A for 1 rupee for 1 year and we compound it infinite times, then we get E rupees, or we get the amount of E. This E is nothing but an irrational number. This lies between 2.72 and 2.71. This is the concept of E, or the Euler's number, and we use this concept in the topics of logarithms in the natural ones. So I hope you understand what is the Euler's number. Let us move on to the properties of logarithms.